Thanks, Nir. It's my distinct pleasure to be able to introduce William or Bill Cooper, who's going to speak to us today. I went through his impressive CV and listed out a few things that I think might be of interest to highlight. Bill is a professor in the Department of Civil and Environmental Engineering at the University of California, Irvine, and he's also, at this point in time, a program director in the Environmental Engineering program at the National Science Foundation, where he's been since September of 2013, and I believe his tenure ends in August. Bill's educational background: he has a Ph.D. From the University of Miami in Florida in marine and atmospheric chemistry. Thesis was on hydrogen peroxide in the oceans. And did his master's degree at Penn State University in geochemistry, and did his Bachelor of Science degree at Allegheny College, also in organic geochemistry. He has a very rich suite of career experiences. I'll highlight just a few of those. He was a professor of chemistry at the University of North Carolina, Wilmington for about a decade. He spent a significant part of his career at Florida International University in a variety of different roles. He's also been involved in the U.S. Army Medical Bioengineering Research and Development Laboratory, and he also served in the U.S. Army, reaching the rank of captain before he moved into his civilian roles. His CV, he has over 200 refereed publications, 50 refereed chapters in books, and he's been the editor or author of 7 books of his own. He's a fellow of both the AAAS, the American Association for the Advancement of Science, and also a fellow of the Association of Environmental Engineering and Science Professors. I found it interesting. I was trying to figure out what to synopsize from all of the many publications that he has. I decided to do the following. I found it very interesting that his first publication in his publication list occurred when he was an undergraduate at Allegheny College, and it was in science. And I also found it very interesting that his submitted recent paper that is being considered by Science is on the, I'll give the title, or at least part of the title, is on the organic chemodiversity of Yellowstone hot springs. And I share an interest in hydrothermal and these kinds of volcanic environments from my own research, but it's very interesting that the organic chemical biodiversity that we find in these kinds of environments are the kinds of things that produce some very interesting metabolic pathways and also probably give us some insight into earliest life on Earth. And so it's quite a variety to have a paper in science when you're an undergrad and then have a paper being considered in science at a distinctly later part of his career. So with that as an introduction, I wanted to basically let Bill take the stage. His title for his talk is Constructed Wetlands as a Sustainable Approach for Treating Emerging Organic Chemicals of Concern. Bill?
Well, thank you very much, Cliff. What he didn't tell you is that I also flunked out of undergraduate college and redeemed myself with my first paper out of Woods Hole on the origin of oil. So I've had a rather interesting career, in fact, actually a phenomenal career, not the least of which was working at Woods Hole Oceanographic Institution. So before I start, I'd like to thank the U.S. Geological Survey and the California Delta Stewardship Council for inviting me here. I'm actually, as I told the people this morning, I'm scared to death because whenever you come here, you never have a clue what's going on, and I realized how little I know about the Delta after having spent the last 2 weekends reading about it. But what I would like to talk about a little bit, and by the way, being a professor at UC Irvine, you know that you're going to get an exam at the end of the lecture. So there's some numbers in there that you're going to have to memorize, some of the reaction rate constants that we've developed. So please pay attention to that. But through a series of events, and I'll try to overview my life since I started school in graduate school in 71, I guess, 69 to 71. But at any rate, I have done a number of different things that seem actually totally unrelated, that when you start thinking about it, all have built up to what I think is the most exciting part of my entire scientific career, and that is looking at constructed wetlands as a sustainable approach to treating emerging organic chemicals. And I'm going to use a couple of examples of pharmaceuticals, which we all know and love in our drinking water. And if we keep going the way we are, we won't even have to go to the doctor. We can get all the medicines we need right in our drinking water, which has some advantages. It has a few disadvantages as well, but nevertheless it has some advantages. So I'm going to give you a short version of the journey here. Then, because I'm an NSF program manager in the area of environmental engineering, I felt that it was important to show the context, within context of my NSF program work and the work that's being done that so I don't fund anything in the National Science Foundation. I only recommend. So when I say I mean the NSF. I don't mean me personally. But I have funded a bunch of programs here in the California area, which I think are of interest to Delta Science. And then I'm going to try to, this is the hardest part because it's a broad range of participants in this seminar. So I'm going to talk a little bit about my recent research and try to show you how, as a result of 15 years in radiation chemistry and another 20 or 30 years in photochemistry, I've brought it all together to look at constructing wetlands, not only for the removal of nitrate, phosphate, and suspended sediments, which is what they're normally used for, but also how we might be able to optimize them for the removal of organic compounds. So, as Cliff mentioned, my career began as an undergraduate at Woods Hole Oceanographic Institution, where I actually published 2 papers. The first one, as he mentioned, was on the fate of, both of them were on the origin of oil. The first one was in science, the second one was in deep sea research, and that served as my undergraduate thesis, actually. I then went to Penn State for doing my Ph.D. in the same field of organic geochemistry, which is the fate and transport of natural chemicals in the environment. And then I ended up having my second impediment, and that was being drafted into the Army. So in case you're wondering, I am a trained killer and also an officer and a gentleman by the act of Congress. So we can put both hats on. So I went to Penn State for 2 years and then ended up getting my master's degree before I ended up going into the Army. And my master's degree was actually on the origin of coal, looking at the Everglades as the modern environment, which was an analog to that 200 and 300 million years ago that led to the formation of, in the Mississippian and Pennsylvanian era, of coal. I was initially stationed at Edgewood Arsenal. Just for your information, that's the Chemical Warfare Center for the U.S. Army, and then Fort Detrick, the Biological Warfare Center for the Army. But in both cases, all I was doing was environmental research. I already told you I was an enlisted first and officer. Then I became a civilian and rose up to the rank of GS-13 in 1980. I had 2 major areas that I was involved in the Army. I have a couple other things that we were doing, fun things. But we developed a test procedure for free chlorine that was accepted in standard methods, and still in standard methods. And you might wonder, why would somebody in the Army want to look at the formation or how you could test for chlorine in drinking water? And the fact of the matter is that in Vietnam, 20 to 30% of the people that end up in the Army's hospitals were as a result of waterborne diseases, not bullets. So therefore, and the reason there was because a lot of times the people weren't actually getting disinfected water because the test procedures that were being used were not specific for what we call free available chlorine, that's HOCl, versus things like chloramine and stuff. That's a whole lecture unto itself, but that's why I got involved in that. And then I ran the Army's program in water reuse from 1970 to 1980, and in fact funded with NSF and the Department of the Interior their first international conference on water reuse. And that was my first Introduction to California Water, because the Orange County Water District was there with Water Factory 21. Takasano from the State Water Board then was also there, and we've maintained friends. And I'm not sure if George Shabanaglas was there or not, but certainly I've known George for, it seems like, forever. So that kind of is what happened when I was in the Army. My academic career, I left the Army and started as a research associate professor at the Florida International University in Miami. And because I didn't have a Ph.D. and I wanted to be an academic, you can't be an academic today without a Ph.D. So simultaneously, I was a Ph.D. student at the University of Miami and got my degree in marine and atmospheric sciences from Miami. So from 1980 to 1987, I had two bosses. I had the Florida International University, where I was a full-time research associate professor running a $300,000 to $400,000 a year research program, and I was a full-time graduate student at the University of Miami. Well, I can tell you that's not the way to do things. It was about 100 hours a week for 7 years, but I survived, and it turned out to be actually fantastic. I then moved to the University of North Carolina, Wilmington, in 1997 and was there for 9 years. I was the chair of the Department of Chemistry and Biochemistry there, and then later when I stepped down and moved to our Marine Science Center, I was a professor of chemistry and marine science at UNCW. Now, one of the unique things that I did when I was at UNCW is I lived on the Intercoastal Waterway, so on the weekends I used to drive my boat to work. Now, that's the ultimate in an oceanographer's life, is to be able to drive your boat to work every day, and that was really fun. Then in 2007, I was wooed away to the University of California, Irvine, to be a professor at the Department of Civil and Environmental Engineering and also a director of an urban water research center. I forgot to mention that when I was at FIU, I was the director of a drinking water research center, or I was acting director until I got my PhD, while I was also that PhD student. That was a crazy time of life. Okay, at the National Science Foundation, I'm the program director for environmental engineering. And my colleagues, who are all engineers, kind of mentioned the fact that, hey, you're not even an engineer. I said, no, but I've run a pilot plant bigger than you've ever thought about running, so that qualifies me as a pseudo-engineer, but I'm in fact actually a chemist. But the fun thing about NSF is, and one of the things that I think where I've made one of the biggest marks, is actually funding a number of projects involved in disasters. So the first one was the chemical spill in West Virginia, and then the coal ash spill in western North Carolina that followed right on the heels of the chemical spill in West Virginia, and then also doing some work on the appearance of 1,4-dioxane in the Cape Fear River and funding a mechanism. And I can talk about these mechanisms later. Right now I'm also working with the same guy that did the 1,4-dioxane. We're looking at perfluorinated compounds in the Cape Fear River, and that's going to hit the fans shortly. I was luckily involved in the Ebola problem, and I say luckily because I think we made a big impact in funding Ebola research, which resulted from a one-day seminar that I was involved in at the Institute of Medicine over at the National Academies. So when the Ebola guy was found in Dallas, you know, he was vomiting and also had diarrhea. Well, you can imagine the people in the wastewater treatment plants were scared to death down there because we knew nothing about the fate of the Ebola virus in water. How long would it last? How would you disinfect it? Was it aerosolized? And all of those questions that a series of my people actually were studying. And we did that in conjunction with Homeland Security, EPA, NIEHS, the National Institute of Environmental Health Sciences, and then Health and Human Services at the ASPR program, which is the program for rapid response on disasters. I funded 5 or 6 people at Flint, Michigan on the lead problem, and we were again, so the thing that's fun about the NSF is we have a mechanism where I can rapidly get money into the hands of faculty members within a couple of weeks. At least I can tell them to go out and start working, and then you'll get the money. And they believed me, foolish them. But I did get them the money. So in Flint, Michigan, I actually, Mark Edwards of Virginia Tech was one of the first federal people to get boots on the ground in Flint. And we had ended up with 4 or 5 projects in Flint and 4 or 5 in the chemical spill in West Virginia. And the most recent one is this Elizabeth Kingia, and I bet you're wondering what the heck is Elizabeth Kingia? Well, it's a bacteria that's actually killed 15 people in Wisconsin. It's kind of like a Legionella that's kind of flying below the radar, but it's actually lethal. So I have a young woman is working on Elizabeth Kingia, and interestingly enough, she's also working with a friend of mine, Jonathan Yoder, at CDC, the Center for Disease Control, who's also interested in people there, and we're interested in how the environmental impacts, the environmental engineering impacts of Elizabeth Kingia. So that's one thing we funded. Now, with respect to Delta Science, I've actually put together a committee in the National Academies which is going to study the grand challenges and opportunities in environmental engineering and science in the 21st century. And what we're hoping is to redefine environmental engineering and science, which will bring it up to date with the 21st century. Interestingly enough, environmental engineering is one of the youngest, other than actually biomedical engineering, youngest engineering programs at the universities. And it's only been around since the 70s when we had the air and the water, the Clean Air Act, the Clean Water Act, and the Safe Drinking Water Act, et cetera. So what we're hoping to do there is to look at what are the grand challenges and what then are the opportunities for young faculty and old faculty alike in environmental engineering. So if I look at specifically in California, many of you have probably heard about our Engineering Research Center at Stanford and Berkeley called Renew It, Reinventing the Nation's Urban Water Infrastructure, and we'll actually be there for a site visit in May, and I'll be there for 3-4 days in May looking at that Engineering Research Center. It's a $40 million investment between Stanford, Berkeley, Colorado School of Mines, and New Mexico State, and so that's really interesting. I funded a workshop in the Community Integrated Environmental Models here at Davis, and then because of my involvement with another interagency group, I met Thomas Harder and mentioned that I thought he might be interested in submitting a workshop for sustainable groundwater in agriculture, an international conference linking science with policy. So we funded that as well. Another one is Doug Parker, who is at the University of California Office of the President. He is the head of the Water Resources Research Institute at the University of California, and he, along with some other, he's not the PI, he's a co-PI, but Doug actually worked in the Chesapeake Bay for 23 years, and I think that that might also eventually inform Delta Science, because the Chesapeake Bay is in many ways similar to, but in many ways different than the Delta issue. Certainly the scale is about the same. It actually is, well, the big difference is there's 3 or 4 states that are involved there: New York, Pennsylvania, Maryland, Delaware, and I can't think of anybody else. All of those are in the Chesapeake, Virginia, of course. And then I have just funded Kathy Jacobs on a workshop Beyond the Colorado River Basin Study. So what we're going to be doing here, this is going to be, there will be representatives from the Bureau of Reclamation, USGS, and DOE, believe it or not, at that workshop. But the fundamental there is to look at the science and engineering aspects of the Colorado. And one of the big questions that really is still unresolved is the connection between the surface water and the groundwater, not unlike something that we would see here in the Delta. I mean, the surface water and the groundwater in many cases are connected, and so that's what we're going to be looking there. And then INFUSE is the next large sustainability program within NSF, and it stands for the Innovations at the Nexus of the Food, Energy, Water Systems. So, and what we funded, and Jay Lund is on this project, the Sustainability Productivity Trade-off, Water Supply Vulnerabilities and Adaptation Opportunities in California's Coupled Agriculture and Energy Sector. Okay, that's going to be a workshop. That's an INFUSE. That's actually a 5-year project. It's, I think, $2 or $3 million. More recently, I just was able to award $100,000 to Jim Tebow, working with Roger Bales at the Southern Sierra Critical Zone Observatory in Merced. And he's going to be looking at Beyond the Brink, a documentary focusing on the water and food nexus and the evolving impact on national security. And the premiere of that film documentary is going to be May 2017. That's coming up at the World Water Congress in Cancun, Mexico. Okay, so my research, as I mentioned, has taken several. I've reinvented myself over the past 40 years several times. So I started out in the Army, as I said, developing a new technique for measuring chlorine in drinking water. But then I got involved in, and I did a whole bunch of other stuff there too, but from a scientific point of view, I got involved in sunlight formation and distribution of hydrogen peroxide in natural surface waters. And what that involved, that was my Ph.D. thesis, where we look at the sun as the source of energy, the natural organic matter in the ocean as the absorber of that energy. It then gets excited to a triplet state. The triplet state reacts with the triplet state of oxygen, which is, unlike most compounds, that's the ground state more or less, and it excites it to the singlet state so it can form singlet oxygen, or it can actually abstract an electron from oxygen and get superoxide, O2 minus dot, which then reacts with itself to give hydrogen peroxide. That was my PhD work. I then got involved in some biogenic sulfur work in the wetlands of Florida, and we actually had a conference at the American Chemical Society and actually published a book called Biogenic Sulfur in the Environment, which rose to be, believe it or not, a bestseller for the ACS. So a bestseller for the American Chemical Society is not really a best-selling book, but at least a lot of people loved our biogenic sulfur story. I've been involved in some very large-scale invasive species projects in ballast water, and with BP, we were working with 2 BP ships, and these are big ships, 850 feet long. They carry 125,000 tons of crude from Prince William Sound down to the west coast, so they stop either here in San Francisco Bay. And just as a story, the bay over by, I think it's the Richland plant they may be going, I'm not sure where they actually, but the freeboard under this ship, 850 feet long, is actually 1 foot when it comes in. So it usually has to stop at Long Beach and discharge some oil and then come up here to San Francisco Bay and discharge the rest of the oil. But when you're discharging 124,000 tons of oil, you can discharge that from those ships in 24 hours. To bring on ballast water to keep the ship from flipping over, on the Tonsina, so we had 2 different ships, the Prince William Sound and then the Tonsina. On the Prince William Sound, ship, there were 2 10,000-gallon-per-minute pumps that would draw water from the harbor and bring it on for ballast. And a 10,000-gallon-a-minute pump will fill up your normal swimming pool in 2 to 3 minutes. So that's a lot of water coming on, and we actually did a full-scale study. The first ship we were using ozone. We actually had over 11 kilometers of stainless steel put into the ship, and BP did that for us along with the diffusers, and we outfitted it so you could use the port side or the starboard side of the ship and actually do half of the ship was a control, the other half was an experiment. So these are really large-scale experiments, but exciting, and we published 4 or 5 papers in that area. And then I've been over my life, because I first kind of thought I was an organic chemist, then I thought maybe I was an analytical chemist. So we've done a lot of work with analytical methods development for pollutants in water. One of the things that we did working with Walt Jennings here from UC Davis, he later became J&W of Jennings, J&W Scientific, where they built the best capillary columns for chromatography, and we actually developed the DB624 column in my lab. That separated all of the 624 chemicals. That's an EPA designation, so we did that. And last but not least, I've sailed around the ocean collecting plastic. Well, the two areas of research that lead to what I'm talking about today was we started to develop a treatment process for the destruction of organic compounds in water, and that involves radiation chemistry. Radiation chemistry in its simplest form is we're injecting electrons into water, the water splits apart, we get hydroxyl radical, solvent electron, and hydrogen atom, which are very, very reactive, and they then go ahead and treat organic compounds. And the other ones might back to my roots in photochemistry, the reaction in surface waters involving dissolved organic matter or natural organic matter. So the research program that I'm most recently involved in is to better understand natural water photochemistry of pharmaceuticals and other emerging constituents of concern. And then to better understand the photochemistry of natural organic matter. So it's this brown color that you see in the water that my mom used to call tannic. You know, oh, those are the tannins in the water. That's the old thing. It isn't really tannins, but it does kind of a plant origin. But it's a really good absorber of light, and that's what you need in order to facilitate photochemistry. Photochemistry is nothing more than the absorption of sunlight photons to induce chemistry, okay? So we're interested in pharmaceuticals, we're interested in natural organic matter, and you can see why that put together was of interest to design and optimize constructed wetlands as a sustainable treatment process. So when we talk about environmental fate of chemicals, you can talk about the chemical, biological, or physical fate. What I'm interested in is the hydrolysis, that is the reaction with water, and photochemical, both direct and indirect. And when I mean photochemical, I mean actually sunlight. And sunlight, at the sea surface, you get sunlight down to 300 nanometers. Our eyes can only see 400 nanometers and above. But the photochemistry, and I had a diagram that I decided to take out because I want to get to the meat of the talk. But basically, I'm interested in hydrolysis because some compounds react with water as a function of pH and temperature, and some don't. And then photochemistry, the direct and indirect. So to scare you just a little bit, this is the equation that we've developed that's evolved over the last 30 years, which I think is reasonably complete for the loss of P, which could be a pharmaceutical or any compound, as a function of time. You have to take into consideration the first function. Oh, let me see, I can use this. So you can see this. The first function is nothing more than the reaction of water with whatever compound you're interested in. The next one is a direct photolysis, that is the absorption of sunlight, and I'll show you this, well, I'll show you some examples. Not many, but maybe not one, well, whatever. The photolysis is where a chemical actually absorbs sunlight and actually is destroyed. Then you have the reaction of what we call singlet oxygen. So ground state oxygen is a triplet. If you excite it to a singlet state, it's about 22 kilocalories. That shows you how old I am. I can't think in kilojoules. But it's about 22 kilocalories above triplet state oxygen, and it does react with pollutants at some very rapidly and some not. Then you can actually also form the hydroxyl radical, which is the strongest radical known in aqueous solutions, and that reacts with many, many compounds. I'm going to show you some reaction rate constants for both the solvent electron and the hydroxyl radical, and those are the numbers that I want you to memorize for the exam. So that's important to remember. Those are really important numbers. Well, one of our major contributions to the whole, and I'm not the only one doing this, there's people all over the world doing this work, but one of the things that we've done a lot of is looking at this triplet state of natural organic matter. So when a ground state of a chemical absorbs energy, it can go up to a triplet state, okay, and a triplet excited state. And a ground state, normally you have electrons that are paired. You know, you all remember the Schrodinger wave equation, right, where you got your little things going down and some things going up like this. That's a paired electron. When you go into a triplet, you've got the paired electrons, but they're in an excited state. They got a lot of energy. And sometimes they actually decompose through what's known as intersystem crossing, which from a quantum mechanical point of view is not legal, but it does it. And then this triplet state, the singlet state can actually, is where they've actually got, or the triplet states actually got, the electrons are not paired and they're highly reactive. So I'm sorry, it goes from a singlet to a triplet. And then we have an unknown here that I'm not going to get involved with. Solvent electron is also formed when we irradiate humics or NOM, And we also get superoxide and hydrogen peroxide. That's what I did my PhD work on. And many, many, many natural waters have carbonate anion in them, and that carbonate anion can react with hydroxyl radical to form a carbonate radical, which is what we call a soft radical versus hydroxyl radical. It's interesting how they tell you what the length of time, the lifetime of a hydroxyl radical is 11 angstroms, which means nothing. But if it diffuses, typically a hydroxyl radical is so reactive that once it's formed, it will only diffuse 11 angstroms from where it was formed to before it reacts. If there's carbonate there, they will react and form a carbonate radical. Okay, so how did we get onto this crazy stuff? So Lipitor, most of you know Lipitor. Just for an example, I forgot exactly what year, but let's call it 2010, 2011. The international market for Lipitor was around $14 billion. So it's everywhere, and so these statins are everywhere. But what we would do, first of all, with a compound, the first thing we did is we would dissolve it in pure water, and we would look at its disappearance with time. In this case, it's 10,000 seconds, okay? And you can see that it doesn't hydrolyze. That means it doesn't really react with water to any great significance at this point. Now, to do this quantitatively, we'd want to do it as a function of pH and temperature, but this is just at 1 pH. Then what we did is we added a known fulvic acid, a humic acid, a natural organic matter. We call it Swanee River fulvic acid. There's a IHHS is an International Humic Substances Society, and they actually sell humic acid that's been isolated from the Swanee River. And when we put that in there and we turned the light on, this is a dark reaction here, okay? We turned the light on, and this Lipitor went away like a shot. So obviously something was going on between the excited state of DOM or whatever it is and the Lipitor, and the result it was that it was losing, we lost the concentration, it disappeared. Well, not, this is the natural log, so it's not three log removal, but it's still, you can see it's going pretty fast. Then the first question was, well, is that singlet oxygen, is it hydroxyl radical, is it a solvated electron? So we did a couple of experiments, and what we did is we took the Swanee River and we added sodium azide. Sodium azide will react with singlet oxygen and take it out of reaction. So if the Lipitor is reacting with singlet oxygen and you remove the singlet oxygen, you should see a decrease in the rate at which it's removed. And sure enough, you did. This is the Swanee River. When we added sodium azide, it went away less, which means, yes, in fact, part of this, and we didn't know how much, part of this decomposition is due to this reaction of, here singlet oxygen is with the pharmaceutical. To confirm that, we then did some experiments in what is known as D2O, that's just deuterated water. And I'm not going to go into the chemistry, but what happened there that confirmed that singlet oxygen was important, the rate at which we lost this Lipitor here was dramatic, and that meant that this reaction was very important. That's the reaction of Lipitor plus singlet oxygen. So that was very important in the removal of Lipitor. So that's what got us going on this whole area. And what I mean got us going, we'd already been doing work in radiation chemistry, so I want you to make sure that you memorize at least 5 of these. These are reaction rate constants, and you can see we've published all of these crazy things. And it's not really as bad as it really looks. I mean, it's actually kind of fun doing this stuff if you don't mind working 12 or 14 or 16 hours a day. So we did a whole bunch of compounds, including DEET, and you can see that the hydroxyl radical, which is the most reactive free radical in waters, reacts at what we call basically these reaction rates are 10 to the 9th. So these are limited by the diffusion. These are diffusion limited reaction rate constants. So as soon as the hydroxyl radical hits any of these compounds over here on the left, it reacts with them. And the actual rate constant we measure out there, in fact, we did all this at the Notre Dame Radiation Laboratory. We could also measure the solvated electron, and you can see it also reacts with a lot of these compounds at a rather rapid rate. And just to confuse you, I put a few more up here, and now to deconfuse you and try to give you a sense of why we did this, I've taken Lipitor and amoxicillin. So what I want to do is I want to deconvolute this crazy equation here to show what the importance is of the singlet oxygen reaction rate with the pharmaceutical and the hydroxyl radical. So what we did is we evaluated what the rate constants were of singlet oxygen with Lipitor and amoxicillin. And you can see that those rate constants are 3 times 10 to the 8th and 1 times 10 to the 4th. So that's 4 orders of magnitude difference. Now, what does that mean as far as the loss of Lipitor? If you only had singlet oxygen in a water and you had Lipitor at whatever concentration, it would have a Lipitor and singlet oxygen, that reaction would have a half-life of 6.2 hours. In other words, singlet oxygen reacts quite readily with Lipitor to remove it from solution. Amoxicillin, which is 4 times slower, actually it's more than that, this is 2, it's quite a bit slower. You can see the half-life if amoxicillin reacted with only singlet oxygen was 5,500 days. So what that does is that starts to mean that we need to know all of these different rate constants in order to look at the fate, the environmental fate of these compounds. If we go to hydroxyl radical, which I've already told you reacts like a shot with many of these organic compounds, we estimate that, well, I should say that we've also estimated the steady state concentration of singlet oxygen at 10 to the minus 13 molar. The steady state concentration of hydroxyl radical in waters that are irradiated with sun with NOM in them, okay, normal natural waters, is about 10 to the minus 16. But the rate constants are so much faster here that what we look is that Lipitor, if it only reacted with a hydroxyl radical, would have a half-life of 67 days and amoxicillin 116 days. So what we do is we start going through all of our compounds, assembling all of the reaction rate constants, and eventually we can then look at this crazy equation. Now, the next question is, what does this equation really do for us? These are actually easy to interpret because they're what we call first-order reactions. That means there's only one reactant. And they're usually, and so let's just say that's simple. The problem with all of these are all second-order rates. That means they're dependent both on the concentration of the singlet oxygen and on the concentration of the pharmaceutical or whatever emerging compound you want. So all of these are second-order reaction rate constants. The way to simplify this entire equation is to make estimates at what the steady-state concentration is of all of these different components. And that was the next step here. And we did that. So singlet oxygen is about 10 to the minus 13th. Now, these are not only our own data, but they're data from other studies in the literature. There's people, Bill Arnold up at Minnesota, Silvio Canonico in Switzerland, and then David Leone in Italy are all doing work regular, and actually in Urs van Gutten is doing some work in this area. So it's not, oh dear, I just hit something, sorry. So at any rate, we need to simplify these so we come up with estimates of these reactive species. The interesting one to me is something that very few people have studied, and that is the fact that this triplet state NOM is 10 to the 13th, which is actually a reasonably high concentration because it's so much of that is in solution. The carbonate radical, I've said, is a rather soft radical, 10 to the minus 15th, may or may not be important. These guys, in general, do not react under normal systems in water, the superoxide and the hydrogen peroxide. Hydrogen peroxide is a very strong oxidant, but we call it, it's kinetically limited. But at very high concentrations, it's a good oxidant. At any rate, so we did that, and then what we've been able to do is that the next step, which is where we're going with the research, is we've developed a series of first-order reactions. So now a first-order reaction is only determined by time, okay? Time. So we can actually then start to make all of those reactions first order, and the only thing that the loss of the chemical depends on then is the sunlight, okay, and the depth of penetration of the sunlight. So in order to do that, it's going to take a lot more work. We've done it with hydrogen peroxide and singlet oxygen, and that is looking at the depth dependence of that in waters. So that's where we are in that study, but I think that has a direct relationship to delta science, in that one of the things that we were chatting about this morning is the concept of actually developing wetlands like the YOLO bypass, where we actually put water out there at relatively shallow environments, and we could have sunlight actually going through that entire water column. And what we would be doing then is not only we can also be killing bacteria and viruses and stuff like this, but we could also be getting rid of pharmaceuticals. And I think that's one of the potential opportunities here in California. Now, future issues. This is one that's very contentious. In fact, I floated this at the Orange County Water District about a year ago and got boos. I said it's about time that we stop thinking of these droughts as droughts. If you believe the climate models, these droughts are going to last for hundreds of years because, in general, the southwestern United States is going to get less water and the northwest is going to get more water, but over time we're going to have, so the question is, should we call this a drought, which implies that it's going to change in our lifetimes, and it's probably not, except it's going to get drier and drier, or should we just recognize this is the new norm? Another issue, of course, everywhere, in California is the same, is how is, with a projected population increase of 50 million in California, how is that going to impact the Delta and the state of California? I think that's a huge issue. I've already mentioned at the National Science Foundation, we're looking at the food, energy, water nexus as the next big sustainability program within NSF. NSF runs programs about 5 to 10 years, and then we jump onto something else. It used to be SEAS, where we had a program called Water, Sustainability, and Climate. And from that, all of our investigators around the country actually came up with this idea of the food, energy, water. At the same time, it was being touted at NOAA, Department of Energy. Department of Energy was the water energy nexus. Agriculture was the water agricultural nexus. And we then said, you know, we need to look at this as a whole system, and we need to think of the food, energy, water systems. So I don't know if you can see this, but this is why I don't like calling it a drought. This is, and why on earth would we care up here about the level of Lake Mead? And I think we do care. But this is 1999, 98, 99, and you can see that the level of Lake Mead has been steadily decreasing. You can see there's a blip up here. That's the, well, this is the atmospheric river of 2010 that hit in Southern California, dumped 10 inches on Orange County. I don't know that that one actually came up here so much, but it did certainly get into the Sierras and lower Sierras and dump a lot of water there, which ended up in Lake Mead, so the water bounced up. But you can see even since then, it's a pretty steady decrease. So I think that there's something to be said for recognizing that we are going to be in a drought, and if that drought may not be the same in Northern California as it is in Southern California. And why do you care about Southern California? Because the Delta feeds 50% of the water that's imported in Southern California. So Southern California, from Santa Barbara down to below San Diego there, Tijuana there, has an economic engine of about $880 billion a year. Yet, to feed that engine, we import 60% of our water, 30% from these are rounded figures, 30% from the Delta and 30% from the Colorado River. So if that Colorado River dries up, as it's certainly projected to, it's not going to be real fast, but it's going to dry up. Where are we going to get that rest of that water to feed Southern California? Well, before questions, I think one answer is direct potable reuse. I'm a proponent of direct potable reuse. I think that's the way that we can get out of a lot of problems in Southern California. We've certainly shown at the Orange County Water District that it's possible. They right now produce 100 million gallons of water a day which is very, well, it's much better, much cleaner than potable water, normal potable water. And I think if we were to look at water reuse, that might significantly decrease the amount of water that we have to supply to Southern California from Northern California, and that would actually facilitate that. So I'm just at 45 minutes, so I want to close. But just to show you that I have a lighter side of me as well, my hobby is butterfly photography. I have a photographic show at the National Science Foundation right now and have given 2 lectures there and also at the Smithsonian on the butterflies of Iguazú Falls, Argentina. So if you get sick of looking at the rain out there today, we can just leave this picture up and you can just imagine yourself with that beautiful butterfly flying around. Thank you very much.
Questions for Bill?
Rainer wants to ask one.
Bill, has your team looked at what happens with these compounds of emerging concern, or the pharmaceuticals, once they get oxidized or whatever?
So we've done a lot of that work using radiation chemistry where we can use a clean solution of the pharmaceutical, whatever it is, and the hydroxyl radical or the solvated electron. And we've done some reaction mechanisms to look at the degradation. We have not done that with photochemistry because we're not at that point. But that's the critical question. That's an excellent question, because when you are using destructive technologies, no matter what it is, you always have to look at the byproducts. And I learned my lesson about MTBE, which we all know and love, methyl butyl ether, which was the gasoline additive. I decided to do a comprehensive review of the radiation chemistry of NTBE, and after 120 pages of writing, 23 figures, I came up with a reaction scheme that was 289 reactions, and some of which are more toxic at the very end, at the beginning of it, than MTBE. The interesting thing about pharmaceuticals, the goal would not to be to decrease them to 0. The goal would be to convert them to a compound that's biodegradable. And so, for example, if a lot of times they'll add a fluorine or chlorine or a bromine to a pharmaceutical to make it stable, okay? But if you can get it out into the if you can get it out into a river where you've got sunlight and DOM, you can actually dehalogenate that and actually replace it with an OH, and it becomes much more soluble and it becomes much more biodegradable. So there's different levels, but that's an excellent question, and it's I'm glad you raised that, because that's always the problem when you're doing destructive technologies versus just adsorbing it on carbon and stuff like that, which then becomes a problem because you got to cart the carbon off, you got to regenerate it and bring it back. Yep, good question. You can see it in their eyes, you know, everybody, you can see that they want to ask a question. Jay.
We have a great wastewater treatment plant here for the Sacramento metropolitan area that is undergoing a new treatment process for ammonium.
Yes.
Do you have any thoughts on that, since you're really quite well versed in a wastewater treatment plant?
Yeah, so that, the nitrogen situation actually was one of the Academy of Engineering's grand challenges is actually not regulating, but understanding the nitrogen cycle. So the problem with nitrogen and phosphorus is they're 2 macronutrients, and you have to get rid of those things in order to minimize the impact on the receiving water. I don't know what process they're using to get rid of the nitrogen, but I know I'm supporting a lot of research on new and innovative treatments like Animox and stuff like this to try to get rid of the nitrogen, because typically what you do in a wastewater treatment plant is you end up oxidizing it up to a nitrate and then reducing it down to nitrogen. So you've got oxidation and reduction going on. And the way you reduce it is by adding methanol, because that's a carbon source, okay? You add methanol, the bacteria need oxygen in an anaerobic environment to get rid of that nitrate. The oxygen on nitrate's is very accessible, so they dump in methanol, make it go anaerobic, and then they get rid of the nitrogen to N2. So I'm not sure in this case what Sacramento's doing, but I don't know. You said they're looking at getting rid of the ammonia? Ammonium. Are they discharging a lot of ammonium then? What are the wastewater? What are the processes that are using? Do you know?
Currently, it's about 20 to 35 milligrams per liter.
Nitrogen.
Of ammonium.
Oh my God.
And so they are going to a coupled nitrification denitrification pathway, which will change the form to nitrate and will reduce the load by about 60 or 70%.
Yeah. So that would be that's a lot of nitrogen, and that's going to actually exacerbate things like harmful algal blooms and stuff like this in the receiving water. And nitrification, denitrification is one way to go. A lot of people are now, we've actually at the National Science Foundation got a whole program together to look at actually making wastewater treatment plants a resource recovery plant where we can recover energy, we can minimize pollution, and we do that by going anaerobically and looking at anaerobic, but we need a carbon source. So what do we use? Food, just like East Bay mud. They're the leaders in that. They were the first one to be an energy neutral or energy positive wastewater treatment plant. But the problem with that is you do end up with nitrogen, and I don't know what source of nitrogen, but you have to be careful. Any source of nitrogen is going to be a problem to the environment, but ammonium's a particular problem. I'm not sure that I really answers your question, but it's a complex one. It's depends on what they're using and why they're going to, yeah.
So let me just go back to the aquatic ecology portion a little bit.
All right.
And so these are chemicals or pharmaceutical properties, and then when they are disintegrated through the process you talked about, what happens to them? Are they beneficial to the ecosystem itself, or say microbes, or are they detrimental to them?
Yeah.
In a way, example that I'm thinking is when I was with Bob Wetzel, he was doing this photolysis of DOC or fulvic and humic acid, and then which would be beneficial to the microbes, which can be broken down into further. So you can get rid of those humic and fulvic acid or DONs.
Yep.
So that could be one question that I have. And also, if that's the case, how the light intensity or the UV intensity, that will affect in the ecosystem that we have or the wetland system that we have a high turbidity, and how would that affect this process you're talking about?
That's a complicated question. We got 2 or 3 questions in there. Let's first of all deal with the easy one. That's the turbidity. The turbidity is from our perspective in general, turbidity, you can't see through the water, but it turns out that a lot of that turbidity is due to small concentrations of mineral that are actually solid, and you can get reflection. So you actually get a deeper penetration, even if it's turbidity, than you would if there was, not as much as you would if there was no turbidity, but turbidity doesn't necessarily shut off the photolysis, okay? So when you start talking about photolysis of fulvic acids and humic acids, that's what we call dissolved organic carbon or natural organic matter. So there's 2 things there. One is that that's the source of all these reactive species that can go on and react with the chemicals. In general, when you oxidize a chemical that's as complex as most pharmaceuticals are, you actually make it more water soluble, although a lot of them are relatively water soluble in the beginning because you got to get them in the water to get them in your body. But 2 is you oxidize. The key there is to disrupt the aromatic rings and get rid of the halogens that are on there if there's halogens. And the hydroxyl radical will react with a halogen on an aromatic ring and make it either a phenol or a quinone, which can then be more biodegradable. So in general, we're making things more biodegradable, so they'll be of less harm to the aquatic system. But you know, one of the problems with these pharmaceuticals is this whole issue of antibiotic resistance. And every time I hear a talk by Amy Pruden at Virginia Tech, I start crying because it's so discouraging. I mean, you know, they found a lot of organisms in New Delhi, in India, in the drinking water. They found organisms that were totally resistant to amoxicillin and penicillin. So amoxicillin and penicillin. So two of the most commonly used antibiotics, there are bacteria that are resistant to that. Now, these are not bad bacteria, but you can imagine in your mind, given time, that there could be bad bacteria, those that cause waterborne diseases, that could acquire an antibiotic resistance. And if they do that, then we're really in big trouble. And I think that this whole question, and I think that's one of the science questions here in the Delta region as well, because we have places like Sacramento and other wastewater treatment plants that are disposing of their water in the river. So we have to look at that antibiotic resistance. And just about everywhere Amy's looked, she's found it. And there's a lot of people looking at the antibiotic resistance, and I think that's a really big scientific question here in the Delta. How is that going to, I think the antibiotic resistance could affect the ecosystem more than the byproducts of the pharmaceuticals. That's my own personal opinion. I have no data whatsoever to back that up. But that's a good question. Thanks. Questions? Dinner's not till 10 o'clock tonight, so we got plenty of time.
Thank you.
That's it?